Welcome to lecture 1 of week 3. In this lecture, we will complete the microscopic momentum balance. Let's first quickly revise the key points of week 2 lectures, then look at some characteristics of turbulent flow. We need to remember that only laminar flow was considered in the flow problems. What if the flow becomes turbulent? Is the analysis still hold good? To answer this question, we need to know the difference between laminar and turbulent flows. The introduction to boundary layer theory and the friction or drag will be done in the face-to-face lecture. We derived the continuity equation applying the law of conservation of mass to an infinitesimal volume. Equation of motion or momentum or force balance equation was derived applying Newton's second law of motion. Since we consider only one-dimensional flow, we only need to use the respective momentum equation. A point to note: when the readily available equation of change are used to solve flow problems, equation of continuity and momentum balance need to be solved together. Equation of continuity and momentum solved together. The complete Navier-Stokes equations, that is the three momentum equations for any real industrial flow, are very complex because of turbulence and other complexities of flow. But for our study purpose, we consider only simple one-dimensional flow, and most of the terms cancel out because of the assumptions we make, and that is why we are able to solve the resulting equations analytically. But the complete equations are rarely solvable analytically. This is the velocity profile that we derived for the laminar flow of a Newtonian fluid in a circular pipe. Substituting r equal to 0, we could see this is r equal to 0. We could see that the velocity becoming maximum at the center of the pipe. So V Z max is P0 minus PL divided by 4 mu L times R square. And substituting capital R, we can see that velocity becoming 0. This is R equal to R. Which satisfies the no slip condition. And you can also observe that the stress is 0 at the center. because of zero velocity gradient and the stress becoming maximum at the wall. Dye stream is injected into a pipe in laminar flow. We can see the dye stream traveling without getting mixed in the radial direction. This suggests that the fluid layers do not mix in the radial direction. If we can measure velocity at any point A in the pipe, we will observe the velocity to be constant with respect to time. This is the most important characteristics of laminar flow. This is the velocity profile that we derived for laminar pipe flow. As you can see, by substituting values for small r, velocity becomes 0 at the wall, which is small r equal to capital R. And the ratio between Vz average and Vz max is 1 by 2. Vz average is obtained by dividing the volumetric flow rate by area. If the flow rate is increased high enough in such a way that Re is much bigger than 2100, the dye stream will start spreading out in all directions because of the formation of eddies or swirls in the flow. If we can measure velocity at the same point A, the time series will now look like this. Earlier, which was a constant profile for laminar flow. We can see how the flow is now chaotic because of what is known as swirls or eddies. Velocity fluctuates chaotically at each point in the tube. This is the most important difference between the laminar flow and turbulent flow. This is laminar profile. Velocity is constant with time at a given point. But in turbulent flow, velocity fluctuates like this. And because of this, we make a time average of the actual velocity, split them into a time averaged velocity and a fluctuating part. So this line is average, time averaged velocity. So there are positive fluctuation and also negative fluctuation about the average. Because of the highly fluctuating nature of the flow, statistical methods such as time averaging is applied to the equations of change when the flow is turbulent. But analytical solutions are not possible, so numerical methods such as computational fluid dynamics is used to get solutions when the flow is turbulent. This is the equation of continuity for laminar flow of an incompressible fluid. Vx, Vy, Vz are constants with time. When the flow becomes turbulent, Vx, Vy, Vz are no longer constant. They fluctuate irregularly. So they had to be split into the fluctuating and the time averaged part, like this. And when this is substituted into the equation of continuity, the resulting equation of continuity for turbulent flow contains only the time averaged part, time averaged velocity, because the fluctuating parts cancel out because of the positive and negative fluctuations. The x momentum equation for turbulent flow is obtained by substituting the actual Vx velocity, which contains the time averaged and the fluctuating part, into the x momentum equation of laminar flow. As a result of this substitution, we get three new variables. These are called Reynolds stresses or turbulence stresses. And we get three similar variables from the y momentum equation and three from the z momentum equations. So as a result of the time averaging process, which is also known as Reynolds averaging, we get 9 new variables. These new variables are evaluated using what is known as turbulence modeling, which is an advanced topic and out of scope of this unit. This is the equation of momentum for turbulent flow. And the new variables known as turbulent momentum flux or Reynolds stresses are evaluated using one of these techniques here. Analytical solutions of the Navier-Stokes equations for turbulent flow is impossible because there are 9 new unknowns and the number of equations are less than the number of unknowns. So we need to create new equations to match the number of unknowns. With advancement in computing technology, this is possible numerically. By looking at the nonlinear dependence, we can say that turbulent flow needs more energy for the same mass flow rate.